Thank you very much, and thank you very much to the organizers to be able to present some of this work stemming rather from engineering perspective to the mathematical community. So my talk will be on the formulation of Hamiltonian control systems for open irreversible thermodynamic systems. So my name is Bernhard Maschke. I'm from the Laboratory of Automatic Control and Chemical Engineering in Lyon. That's why there's an interest in thermodynamics. I'm dealing mostly with the modeling of dynamical systems, open dynamical systems, and control. So basically the motivation of all this work is to use physical invariance and coupling in first physically based modeling of technical systems, also physically based simulation, you making use of invariance that you can derive from the dynamical model, and control design. So basically we design control Lyapunov functions so that we ensure that in closed loop the system remains stable in some sense. And then finally, we are much, rather than really control, we want to address the design of processes, simultaneous design of the process and the control, and basically using physical analogy, because we are sure that we cannot modify the system so much, so you can more or less program it somehow. Yeah, you can program transfer coefficients, that's the best you can do. And actually, then I was looking full of hope to books in mathematics, and said, well, surely for these simple systems, I have a whole theory, and I just have to copy it and to use it somehow. And then, actually, it's very interesting, because you have a lot of competing formulations. Yeah, and about thermodynamics too, it's not so easy, and it's very understandable, because the models address a problem. Yeah, so depending on your problem, you will formulate it differently. So what is quite clear, and I started in robotics actually, and mechatronics before going to chemical engineering, is from mechanical systems dynamics. So there are a few references, there will be more, so I don't insist on that. But then you use heavily Lagrange and Hamiltonian systems for robotics, for instance, and in control theories of some very old work using these systems. So basically it's the systems that you know, but they're augmented with input-output maps. So you have torques, for instance, and velocities of the joints, or currents and voltage of electrical motors as external variables. So basically first you have an ill-defined problem, you cannot think about the solution, because the solution will depend on the interface variables. Huh? That's the whole design process for engineers. Okay, but well, if you have a robot, you have a series of links, you have a series of motors, maybe the robot interact with a human. So I started working for telemanipulation in nuclear research centers. So you have a robot interacting with somebody. Yeah, so that's not so easy. It's not an environment which you know. You can predict more or less that it will be passive. So operators not so strong. And then you very soon end up with some sort of generalized circuits. Yeah? And in this case, you also get Hamiltonian systems, but you had a whole debate. What is a Poisson bracket associated with the networks? And also maybe something better than Hamiltonian systems, that's a so-called Brayton-Moser equation, when you write a gradient system, yeah, with some names which had worked on that. And all are useful for different purposes. For instance, the Hamiltonian systems, the generating function is mostly the total energy. For Brayton-Moser's equation, that would be the power, for instance, power dissipated and so on. Yeah, and that might be useful for some reasons. So if you want to have electromechanical system, then the story goes on. You have basically what most people write is a sum of a Hamiltonian system with a gradient system. Yeah, somehow. And then in chemical engineering, the same story goes on. So there's a lot of works. I just give a few references. You have models which are gradient systems, and generic system is a combination or sum of a Hamiltonian system and a gradient system. Then you have some pseudo-Hamiltonian system, but there is some really an obstacle because you have some intrinsic nonlinearities due to the balance equation of entropy. Okay, so in general, my perspective to choose the geometry of the phase space is to look to Dirac structures. So Dirac structures have been defined by Alan Weinstein, one of his students. And it's some sort of generalization of both Poisson brackets and presymplectic forms to treat under the same hat symmetries and constraints. And that's very nice for us because constraints is interconnection, yeah, for engineers. Yeah, we take two systems, say some variables are equal, voltages or currents or whatsoever. Yeah, so. And the only thing we did for perspective for control is not to work on this tangent and on these vector bundles, natural vector bundles, which are tangent and cotangent vector bundles, but on more general vector bundles to include interface variables, which we called port variables because of circuit theory. Yeah? Okay. There are numerous applications to control. The one I prefer is using Casimir functions to derive stabilizing control laws, and then so interpret feedback interconnection as an immersion, then I reduce again the system through using this Casimir reduction, or you have some more techniques based on inversion, and then you try to assign the Poisson bracket or the Leibniz brackets and the Hamiltonian closed loop. Okay, and then maybe I would like to stop and to show you some examples where I participated more or less, and they are all infinite dimensional. I will talk on finite dimensional systems, but they're all infinite dimensional. So, for instance, and all these examples went to the experiment. Yeah, so we had the test bank, or we used the test bank, and so this, for instance, the pressure swing adsorption process is a multi-level system. So you have 3 scales. Yeah, and okay, I'm sorry you cannot see the, okay. I just wanted to see it. I mean, this is just a drawing, yeah, so something you can see, how it is built. Then here's some decomposition on the levels, and here we have a network. So we really use a network, and this represents the mass and heat transfer processes in the test bank, yeah? And with this network is associated a Poisson bracket. Yeah, or a Dirac structure more general. Yeah? And this is very nice because we go in a continuous way from engineering, where an engineer doesn't know about what Frédéric or Joël have presented and don't want to know, but then you can use it. Yeah, you wrote all the equations in coordinate, of course. Yeah, and then we have experiments also on the microchannel. So there's a colleague of mine who was in our group, and he works on the microchannel, but then the applications are really irrigation channels, coupled irrigation channels. And again, we have a distributed parameter Hamiltonian model of that. We also have worked on ion polymer metal composites for doing some skins for robots. Yeah, again, you have complicated mass transfer systems. So you have the electrical double layer, your electrostress diffusion coupling, large mechanical deformation. So 3-level systems, you can interconnect all that together, and you have a network. Yeah, we have a circuit. Yeah, and with this circuit, we can use all the theory on Hamiltonian systems, Lagrangian systems. Yeah, and we made some experiment. Some were very nice. For some electrolytes was very nice, and for some other electrolytes, we missed something, yeah, in the model, yeah, but we can correct it. And we can reuse. So this model's electrolyte was reused from another project on fuel cells. Yeah, so we can reuse models. We have networks, we can compose them. So that's the idea. And then very proud, even we had a WIZ experiment on the Tokamak in Geneva, we had a model thermo-hydrodynamical model, and again with a network. Yeah, and the different domains, the colors are the different domains. Yeah.
You said you had several scales in the model. How do you implement the scales in the networks?
Oh, we have a coupling element, yeah? Because basically what you have a fiber bundle structure of your independent variables that we have seen with Frédéric, yeah? And then we use that.
So they are coupled.
Yeah, yeah. But so it's quite, I mean, it's not very complicated, but you have to use this fiber bundle. So you have, on one scale, you have one point, and at that point you have several dimensions on the lower scale, yeah? And you can write couplings very easily. Say the total flux, if you have a sphere which you reduce to the point, you can at the lower scale, you can just couple it by computing the flux through the local surface, yeah? So this is, but it's nice, huh? Because we can really, and this is again, this defines a Dirac structure, yeah? Some sort of Poisson bracket and so on, yeah? Integral relations. And here again, we have this tokamak, and you can see the electromagnetic domain, the Lorentz Joule effects, the material domain, the heat flows, and so on. And then we get the network of that. We can write a simulation model, which is, again, numerically symplectic. Yeah? So we use symplectic integrators. And we compare it here with an experiment. Yeah? So, just to show, I mean, that why I prefer this network approach, and to associate networks with Poisson brackets, which can also be differential operators or integral operators for the multi-scale coupling. Okay, so this is very nice. So why do I still could get the impression that I understand the topic? But I mean this. So there were several application control there. I couldn't. Yeah, but I mean for thermodynamics, there's something intrinsically wrong because of the entropy balance equation, entropy creation term. So this linear structure for Dirac structure of Poisson brackets vanishes. Yeah, so you have a tensor which depends not on the point on the fiber, but on the elements of the fiber. Okay, fine. And when I came 16 years ago in this lab and learned about chemical engineering, so I thought it would be very simple to find the equivalent of mechanical systems. And then very early I was inspired by the work of Miroslav Grela and Murugawa. So two different works completely, but what they use is the intrinsic geometric structure associated with Gibbs equations. Yeah, so my talk will be how to translate what we know about mechanical system to this thermodynamical phase space, yeah, which has an intrinsic structure. And then my goal is then to use it for control. I will show it later on. So I forgot to do the sketch of the talk, but you can see it on the left. So first, the geometric of thermodynamics and the definition of control contact systems. So Hamiltonian systems define contact manifolds. And then some early result on feedback and conclusions. Okay, something very well known. First, you start with the thermodynamic properties of a system. Yeah, so equilibrium thermodynamics. Yeah, so this gives actually the structure of the thermodynamic phase space. So it's very well known. There will be some very famous reference at the end. But actually, in our labs, it's really a problem because the property of matters are extremely diverse. It's very complex if you have strange mixtures of all kinds. And you have really it's a whole thesis to determine for these structures. You have a series of experiments to do. So it's not at all like the kinetic energy in mechanics, which is just a quadratic function. You don't think about it too much, yeah? Yeah. So this is actually a whole topic, but for mathematical perspective, it's very easy, well known since now more than 100 years. Yeah. And basically, how you describe that, you have n plus 1 extensive variables and n intensive variables, and they're related by Gibbs relation. Yeah. As are related by Gibbs relation. And this already, this Gibbs relation, gives a canonical geometric structure because it's a canonical one form. Yeah.
In thermodynamics, the P are function of the X. The P, they are explicit function of the X. So
yes, but this is Gibbs relation which tells you that. Yeah, that Gibbs relation will be that dx minus sum of pi dxi is 0.
So it's not contact.
This is a contact form. Yeah. Okay. I will show it later. Yeah. So it's how to express these relations. Yeah. Yes. I will just explain it. Yeah. But this is basically what is the contact structure stemming from. Yeah. But I will be. So if you read to Gibbs' work again, so it's more than 100 years ago, then you have Gibbs' fundamental relation, which tells precisely what you say. So basically, you have just extensive variables. Yeah, you have a set of variables, which is the energy x0, and then some n extensive variables x, and then you have just a definition of the energy. Yeah, you say that x0 is a function u of x. Yeah, and this is what I hoped to find when I came to my lab, but this was written nowhere. You have a lot of other relations, but not this one. Yeah, what you have actually. And I took the picture from the PhD of Benayoun. I was too lazy to draw my own, just to say. So, but actually, what you find in all this book, what is a matter of measure, is not you cannot measure the energy. What you can measure is a differential, yeah, because you put some system in equilibrium, yeah, and then you do a measure of temperature whatsoever, yeah, chemical potential or so. So here you go back, so you, in fact, the thermodynamic phase space in your term is a space of one judge of functions, real valued functions. So basically what you get with that is that you consider n intensive variables, which are conjugate to the n extensive variables. And then you write that Gibbs relation is satisfied. Yeah? Yeah, so write that it's satisfied. But then the first curve becomes now, I had the curves of one variable that becomes a submanifold of a three-dimensional space. And this will be the actual thermodynamic phase space where the dynamics of interest is taking place. Yeah, so it's very well known. If you take a simple thermodynamic system, then you can give names to the extensive variables, the energy, the entropy, the volume, the number of moles. Yeah, if you add systems, you add these quantities. And intensive variables describes the equilibria. Yeah, temperature, pressure, chemical potential. And Gibbs relation relates all these variables. So this is what you find everywhere, all this, as data. Yeah? So not at all Hamiltonian or Lagrange or whatsoever. Yeah, you have very complicated formulas. It's not easy to integrate at all. Yeah? So I was quite desperate about that. Well, not desperate, but I mean, there's different habits. Okay, and this it's okay, I just took it, but you know all that. So basically, staying from this Gibbs equation, yeah, then you can say that define a one form, and it's actually, if you look, it's a contact form, which I would maybe just skip this slide because it's more for engineers than for mathematicians, but you consider a thermodynamic phase space equipped with a contact form. This stem back, so I have just a few inspiring references. Okay, so this from, yeah. So in practice, what you have, you do not use really the internal energy, but some other chemical, other thermodynamic potentials, and that basically where the Gibbs equation is valid defines the Legendre submanifold of the thermodynamic phase space. Yeah, very well, and there are some means to define it. For instance, if I take the pure monoatomic perfect gas, yeah, so then I take Gibbs form, theta, and then I just take the free energy as generating function. So I take as independent variable now T, the temperature, the pressure, and the number of moles, so mixtures between extensive, intensive variables. Then I can find, just applying the definition of Legendre transform, I can find all the state equation I need. Yeah, the first one I find is a very famous state equation of perfect gas, but the other ones are as valid as the first one. Fine. But I'm interested in dynamics. That was again very easy. There was some work lying on the, just had to read it by Mrugawa basically, and by Miroslav Gremla. First about reversible transformations. And actually what you would like, if you describe dynamics, you would like something which keeps invariant the Gibbs form, just a thermodynamic system remains a thermodynamic system along the time. And well, then you end up to, it's very easy to consider contact vector fields, yeah? And this, just as a Lie derivative of the contact form is, I would consider it's not really zero, it's rho theta, so the distributions are invariant. In fact, for physical models, it's zero. Yeah, for every practical model I have, it's just the form itself is preserved. Fine. So it's just Hamiltonian vector fields on a contact manifold, and they're defined by this. Well, in coordinates, like I like to write it to understand a little bit, it's almost like a Hamiltonian vector field in the classical sense. So here you see a part which depends on the differential and with some sort of bracket, and then you have one part which depends directly on k, on the generating function. Yeah? This corresponds to the vertical plus the horizontal part with respect to theta. Yeah? So basically you can prove that the tangent space of the contact manifold can be decomposed into the kernel of d theta and the kernel of theta. You have two formulas, and for contact vector fields, oh sorry, I changed k to f. If f is the generating function, then you have this formula. The Hamiltonian vector field xf is f times the Reeb vector field, so it's d over d x0, plus something which is like a symplectic standard Hamiltonian system. Okay, and in the case where f is an invariant of the Reeb vector field, so the Lie derivative of f with respect to e is 0, then you have a very much more easy decomposition. xf is fe plus theta perp df, the differential. Okay. Fine, so that's nice. You see, and the nice thing is also because the Hamiltonian vector field depends directly on E. Now you have an isomorphism between functions and contact vector fields. Yeah, depends not only on df, but it depends on f. Yeah. Okay. Well, but this is well known. I don't tell you something new. And Mrugawa, he showed the following thing: is that yeah, what you also would like is during a thermodynamic transformation, that the perfect gas remains a perfect gas. Yeah, or van der Waals gas remain. So what that means that the Legendre manifold should be invariant. Yeah, you describe a motion on the Legendre manifold, and that just means that the generative function k, so the Hamiltonian function, vanishes on this Legendre manifold. Yeah, and then this submanifold is invariant. Okay, fine. And reversible transformations, that's this very nice result from Mrugawa, that the generating function, the Hamiltonians, are just the state equations. So for instance, I take as generating function k u minus 3/3 of nRT for a perfect gas. Then it's very easy to, I get the contact vector fields, it's very easy to integrate it in this case, very simple, and you get the isochoric closed transformation. Yeah? And these are the celebrated diagram you all computed with your professor of thermodynamics. Yeah, you know this mysterious reversible path to compute, yeah, the properties at the end of start and the end of a transformation. Yeah? Very nice. So this is very nice, just as control. So here are a few. They wrote much more, but I just put a few references which I selected. But I was interested, of course, in chemical engineering in irreversible transformations. Yeah, so I looked everywhere, and I missed one reference. Frédéric gave me later, but I don't read all the journals. I missed it, even with keywords of all kinds. So basically, you want to represent mass transport, for instance, through diffusion, heat transport, and all other kinds of systems, and also mechanical and thermodynamic systems, and tokamak, and whatsoever you like. And therefore, I suggest the conditions are the same. Yeah? So I invented names, or we invented names. So we say conservative system on the contact manifold. Well, you have to have a thermodynamic phase space M equipped with a contact form, a Legendre manifold, which describes the properties, equilibrium properties of system, where the system evolves actually, and then a contact vector field, which is generated by K0, that should be K0, and which satisfies the invariance condition. Yeah? Now, if K is a state equation, then I get reversible transformations. I will give you some, and then the differential equation to integrate. So this is nice, but you see that.
Why do we have a K and a K0?
Because it's a typo. Okay. Until now, the notation is still simple. Why it's K0? But because this will be the drift vector field. Yeah, then I will have control vector fields. So 0 is for the drift. Okay. And I will give now some examples. What is missing, I take the conclusion before, I cannot give a characterization of K which corresponds to a thermodynamic process in general. I don't know how to define that. Yeah, so we shall see that I do a construction. I lift to the thermodynamic phase space a set of balance equations of extensive quantities. Yeah, but I have no idea how I should be able to say if you take this K, like the Legendre manifold. I said nothing, but actually you know that U is convex, yeah? Or S is concave for a monoatomic gas. I didn't write it yet, and you can combine it with so there are theories where you have a metric on this Legendre manifold generated by the entropy function, for instance, but they didn't do that. In the same way, I will show you some examples. So the basic example, which is the analog of the mass spring system for Hamiltonian systems. Yeah. So here you have two compartments which can just exchange a heat flux. Yeah. So that's the basic. So basically, I will write. I have the internal energy of each compartment, the entropy, and the temperature, and I will write I want to write the entropy balance equations. That's very easy. So the thermodynamic properties are given by some function u, or given by Gibbs relation. du is T ds. So T is du over ds, with some u, with nice properties. And then I have the heat flux. I call it q dot, but it's a very bad notation. It's lambda T1 minus T2. Yeah, so Fourier's conduction law. And then by the continuity of heat flux, the heat flux starting from 1 is going to 2. I can just write that the heat flux is the product of the temperature times the time derivative of the entropy. And then I get the two balance equations, yeah? So you see, I cannot write K directly, yeah? I go back, yeah. And, okay, I'm not the only one to do that, by the way. Yeah. And then I take as contact Hamilton is a pointer. No, it's not a pointer. Here, the contact Hamilton, you see, is some function R, which is this one, times a bilinear function between P, the coordinate of the temperature, and the coordinate restricted to the Legendre manifold. So I have P transpose GST. Yeah. In front of that, I have something which defines the irreversible phenomenon. Yeah? So lambda P1 minus P2 over T1, T2. Yeah. Okay. So this term resembles very much the lift that you do of a dynamical system. Yeah, for optimal control problems. You have P transpose F. It's precisely what I've written. And then in front of that, I have precisely the nonlinear term, which allows me to get the entropy creation term. Yeah? So the nonlinearity which says that sigma will be positive. Okay. So now I write the dynamics on the whole harmonic phase space, not only on the Legendre manifold. Yeah? So I get something very complicated, but you see there are a lot of terms which vanishes when I have the Legendre transform. So P transpose G du dx is 0 on the Legendre submanifold because P is du over dx and G is Q-symmetric. It's just 0, 1, minus 1, 0. Yeah? G is a standard symplectic matrix. Just say that you have two compartments which exchange heat and are in equilibrium. Yeah? So it's a sort of very strange oscillator, yeah, which is modulated by a function which gives him completely different properties. The solutions are completely different. Yeah, and this is this term R. Okay, and I get a lot of things, but I'm interested only in the, oh, thank you. Beautiful. I'm only interested when I restrict this dynamics to the Legendre submanifold, yeah, because there's where the actual system is evolving. If I do that, I get the energy balance equation, yeah, there's no exchange with the environment, it's 0. I get the local energy balance, that means expressed on the temperatures, and with just applying the definition, then there's nothing, and then the entropy balance equation. Yeah, and then I see here what I said, and the entropy balance equation is very funny because if you would have just this term, to d is du over dx, you would have a mechanical oscillator. If I add this, which is, yeah, I get something completely different. Okay, there are a lot of, okay. But I'm interested in control. So now I have to introduce, I will do that in a very naive way first, external variables. For instance, I want one cell to be heated by a heat flow, external heat flow. Yeah. Then I say, okay, very simple. I will define the drift term. So I have again a Legendre manifold of a contact manifold. And here I took the trivial case, but I don't know why. And I have K0, which is internal Hamilton, describes the drift dynamics, and Kg, which are Hamilton, describes the interaction with the environment, like in physics in general. And they all satisfy the invariance conditions. They all vanish on the Legendre manifold. And then I have this differential equation. So x tilde dot is the drift vector field, which is a Hamilton contact vector field, plus some linear combination of the interaction contact Hamilton vector fields with some what you call parameters, and we call it control. Yeah, that's where I will have an action on the system. For instance, for a chemical reactor, we control the heat flux through the jacket. Yeah, fine. Here, so I take this simple example. I have the two cells again, and I have here a wall which is open to the environment, and I have sort of thermostat. I can control the temperature of the thermostat, T exterior. Yeah. Okay, and what happens if I do that? Then I have the same dynamics. I write the two entropy balance equations. This is what I just described here. And then I have plus here something which is lambda E, so it's very complicated. Actually, it's okay. If I multiply by U, I don't know why it's written like that. Preferably look to that. I have lambda E 0, 1 plus 1 over T2 U, and U is a heat flux. Yeah, forget about that. Okay, so I have now a term which is affine in the input, which is external temperature. Okay, I can lift it again. I can lift the whole thing like I did it before, yeah, by pre-multiplying, by defining a contact Hamilton system, which is with a control contact Hamilton, which is again something like P transpose times the control dynamics, the input dynamics. Yeah, here I do the same. So you see this vanishes when P2 is equal to T2. This term vanishes. Kc is 0 on the Legendre manifold. Beautiful. So I can write the equations. I obtain something very classical. Yeah, again, but with some input terms. Maybe you are not so fond if I do the details on the continuous stir tank reactor, but for our lab it's very important. But I will just make it very rapidly. So here just look for one. I imagine I just have one reaction, but you can do that with several reactions. So I have here's the stoichiometry of the reaction with the stoichiometric coefficient, nu1, nu L plus 1 to nu m. And I assume, like before, that volume is constant, pressure is constant, so it makes things a little simpler. And basically, you see that the dynamics, so I will now write the balance equation on the extensive variables, so the number of moles of each species and the entropy. And then I get an expression again, like the completely equivalent to the previous one. But G is now a matrix depending on the stoichiometric coefficient. So this is a network. Maybe you know the work of Oster and Peresson on the dynamics of chemical reaction networks, which is very used in biology now, in cellular biology. It's very used. Yeah, and then the stoichiometry. So instead of having the symplectic matrix 0, 1, minus 1, 0, we get here a matrix which depends only on the stoichiometric coefficients. And here again, I have a term, modulating term. So there's a constant skew symmetric matrix, and I have a modulating term which I have the velocity of advancement of the reactions, volume, and the temperature. Beautiful. So I now lift the whole thing to the thermodynamic phase space, and I can write, you see here, the contact Hamilton with the same trick of lifting the balance equations. Beautiful. Okay, and then, based on this very, very naive way to describe things, there was a very nice paper by Joachim Berger, and he generalized the whole thing in a way you probably like very much, because a lot of bundles of all kinds, and it's intrinsic and it's more general. And he's just using an alternative definition of contact vector fields, was a contraction of the vector field with theta is k, yeah? That's the vertical part, and the contraction of the vector field with d theta is now dk applied to the horizontal part of the vector field. So basically something like that. Yeah. Okay. And now you will have a definition of control system you probably like much more than what I have done. So basically, so it stems from some variational calculus. I skipped that, yeah, so the whole definition. And so he introduced what is called output variables, which are the observables of the system, and input variables, yeah, which are the control. And they are conjugated, like intensive, extensive, yeah, also. And so this is what I said. You can consider a vector bundle over M. Yeah. Then you have a bundle map A from the cotangent space to E to the output. Yeah. And then you have conjugate input variables, which is in the dual, of course, of the output vector bundle. The input map is the adjoint of the output bundle map. Then you have again an internal contact Hamiltonian function K0, which describes the drift dynamics. Yeah, and then the dynamical system, dx over dt, is equal to some vector fields, which depends on the state, thermodynamic state, and the two additional variables. This is really a control system. Control system, you don't have y. The systems depend only on the control and not the observation. Yeah, so this is something, a variation, and then this satisfies the two. Yeah, so basically x minus a star u should be a contact vector field. Yeah. Well, and then you have a very nice thing here, that the contraction of x with theta is an energy balance equation, basically. Yeah? I forgot to say that K0 is actually a virtual power of the system. So you have here the power plus the power inflowing through the boundary of the domains, yeah, which is precisely the vertical component of the vector field. Yeah. Or I'll repeat it, so this is not necessary. Yeah, and then I wanted to have to compare it a little bit. and to have a more explicit definition. Yeah, so the vector field actually is a drift contact vector field, like I had defined before, yeah, plus a term which is linear in the input, but plus a term which is related to the incoming power flow here. And what is y? Yeah, u is free. Yeah, u is a free parameter, but y is a function of the state and is a function of the solution, unfortunately. Yeah. So it's not like we use, so I was very depressed there. It's not something I can solve with the tools of normal tools of automatic control. Yeah. And the output variables should satisfy also a differential equation. Yeah, so I have to solve the system to know the output. So it's not something usual to us. And then I rewrote the whole thing in a more understandable to me form. So what you see, dy over dx is just a applied to dk0. So this is what I expect. I expect the adjoint. I expect that somehow the time derivative output is the image through the adjoint to a star of dk0. This I expected. Plus here is q-symmetric term. D theta is q-symmetric, depending on u. Yeah. Okay. But it's not completely. I still have to compute solution. I don't have a function. And okay, then I take the particular case of the definition I had, which is valid for all the model I use in chemical engineering, where the input map A is defined by using these contact Hamiltonian vector fields here. Yeah? So A of lambda is just the product lambda and the horizontal part of the interaction contact vector fields. Okay. Yeah. And then, I should have a conclusion, which I dropped. Oh, sorry. I should have written it better. In this case, the output y, I don't have to integrate. The output y is k, is directly the interaction contact Hamiltonian. Yeah, it's ky in this case. Yeah. Okay, and we came to the same conclusion. What is the observable associated with this input? I mean, this control linear in the input control contact Hamiltonian vector fields by considering. Okay, yeah, I would like to mention the work of Balian, which I didn't know, but which who treats in particular these two cells exchanging heat, and actually he uses has no much better idea than me to find a K, so he just uses lifting. And I would really like to know how can I say that I have a thermodynamic irreversible phenomena just by looking to the function K. That's but including plasticity, please, and all kind of things. Yeah, because this is the case, I show it's the case of irreversible phenomena near the equilibrium. I have a linear relation between the flux, yeah, and generating force, yeah. Yeah, and you can see that in this quasi-bilinear structure. Okay, then there are a lot of work, and I also the work on Geometrical thermodynamics, which adds the idea of having a Riemannian metric on the Legendre manifold induced by the entropy, for instance, or minus entropy, and so on. Okay, I would like to show some result on feedback invariant. So, well, I'm working on automatic control. So what you have, this variable u, the input. You look for a function of the state or observable such that in closed loop you have better properties, stability or whatsoever to some point. But first, I look to what are the feedbacks, so the function u of x tilde, which leave invariant the structure of the system. Yeah? If I put any feedback, then the whole thing is lost. I just have a dynamical system. Yeah, so under which condition on the feedback is a closed loop system again a contact system? Okay. I just write it. Remember, okay, I'll just recall the definition of a control contact systems are fine in the input u. So now I'm looking for a function u of x. Yeah, I look for a function. So I took the single output case, but you can do it in multiple output too. So a state feedback is just a function alpha of x tilde. And I just wonder in which case xk0 plus xkc alpha of x tilde is again a contact vector field. So I just take a section through the distribution defined here. Yeah, I wonder if this corresponds somehow. Well, it's very easy to show that only solution is alpha is constant. So then we got depressed. But, okay, it's just a virtual system. Huh? We look to design. Yeah? We just want to have ideas to make the synthesis of a nonlinear controller. Yeah? So we say, well, I mean, who cares about original Gibbs form? Let us change this, so let us modify it. Proof, let's skip the proof, sorry. Yeah. Yeah. So maybe there exists some modified contact form such that the closed loop vector field is a contact vector field. Yeah? And this we do already for mechanical system. We modify the structure matrix or the Poisson bracket. And basically for us that means that we do short-circuiting some flows of power. Yeah? For electrical motors we say, well, I will short-circuit virtually through the controller the power somewhere, and that might have a lot of advantages. Okay, I do the whole thing, and I skip all the details. And in control, it was very nice, we do wishful thinking, like any politician. Yeah, so we have to do the design. So we look for some feedback, u of x tilde, such that maybe the system satisfies. So now I look for a feedback such that I get in closed loop a strict contact vector field. Yeah, and then I just get a condition. Yeah, so alpha is a feedback, theta d is a closed loop contact form, and I get a relation between two things. So if this has, so I have too many variables. It's an underdetermined system. I have theta d and alpha to choose simultaneously. Yeah? But this is a design parameter for us. So design parameters will be, for instance, theta. We need this degree of freedom, else. Okay, and as we are very bad in integrating equation, we just took the simplest solution. We say, well, theta d, maybe we would like to have that it's theta plus an exact one form. And then this is, you can show that this is again a contact form. Yeah? And if we do that, this matching equation, so we skip the proof. The matching equation becomes much more simple. Yeah, so now we have a matching equation in F, which is dF, which is the difference between the open and closed loop contact forms. And we get again a matching equation. So we have to find alpha and F which satisfy both things. This equation, sorry. Very good. Yeah, and basically what is interesting to us is that actually we have a degree of freedom now. So this feedback should be just phi of Kc, so the interaction, the control Hamiltonian. Yeah? And this is a result which is very classical for controlled mechanical system. It's the same. I can change the potential, so to say. Yeah? Very classical. And then K, the Hamiltonian in closed loop, is K0 plus phi, which is the integral of this small phi Kc. Yeah? Yeah, so now I have a design parameter, which is phi. I can not do so much, but I have a design parameter. Yeah? This is what I look for. And actually, it's quite easy to solve. You have a quasi-linear PDE to find the F. Okay, just now I have structure-preserving feedback. But usually I'm interested in stable system in closed loop. Yeah? A chemical reactor is a very complex system to stabilize. So this is just some games for the moment, yeah? Just games. But I would like to know if I can stabilize it, because else I can throw away all this work. Yeah. Yeah, and first, then you should know somehow something about contact vector fields, the properties in terms of equilibria and stability. So this exists, you can copy it from different books. So how is an equilibrium defined? Yeah, it's that k of the equilibrium point is 0 and dk of the equilibrium point is 0. You can find that in every good textbook. Very nice, so I can characterize the equilibria of a contact vector field. But remember, I know there exists a Legendre manifold which is invariant. So k minus 1, 0, where are all the possible equilibria are in the inverse map of 0 by k minus 1, inverse image. Yeah? So this submanifold should not be void. And I will just assume that it's some regularity assumption, yeah? So it's at constant dimension 2n first. Yeah, so it contains all equilibria and it contains, of course, all the Legendre manifolds defining thermodynamic properties which are compatible with the system. Very nice. Yeah, so basically, but I also know, if I have string contact vector fields, that actually I have a foliation of invariant manifolds of dimension 2n. So I cannot stabilize completely the system, but I'm not interested in stabilizing just on one Legendre manifold. Okay. Yeah, this is what is said here. Sorry. Yeah, so any k minus 1c is invariant manifold, so I'm just interested in one. Yeah. And then I looked somehow more. I thought everything is written, so maybe I miss some books. I do not read all textbook on the subject. Yeah, but I thought maybe there's something written about equilibria. Yeah. So actually, I couldn't find something, but it's not very complicated to prove it. Yeah. So now I restrict the stability. I mean, the quest for stability properties to this invariant manifold, k minus 1 of 0. And if I have I'm interested in having a hyperbolic point, yeah, and stable, yeah. So I look to hyperbolically critical points, yeah. And then what happens is that the stable manifold and the unstable manifolds are both Legendre manifolds of the thermodynamic phase space, yeah. So like for symplectic manifolds, with Lagrange manifolds. Yeah. So, I mean, I thought it would be written, but maybe it's an exercise for third-year students in mathematics. I don't know, so I did the exercise, and, well, I mean, it's very classical. We skip it here. It's nothing very well. Okay. So that means that, indeed, I have now a chance of stabilizing a system, but not on k minus 0, just on this Legendre, on the stable Legendre manifold. Yeah, I cannot stabilize it completely, but that's enough for me. Yeah, because I had an n-dimensional systems and independent balance equation. Yeah, and I want to have an equivalent closed loop, stable. So I know I can achieve that. Not a big surprise, but I know it. Yeah, so I can find a feedback. Yeah, such that the system closed loop is equivalent to this dynamics on the stable submanifold S plus, which is a Legendre submanifold, yeah, which then I have an equivalent physical system for that. Yeah. So I combine the two theorems. I take an example. Yeah, so now I take again these two cells. And I just recall the contact, the internal and control contact vector fields. Yeah, so here the input is the temperature of the thermostat outside. So I assume I can control that very rapidly, and I do all the computations. I solve all this simple PDE. And I get a result which I expected somehow, which I'm happy to find, an expected result, is that basically the control alpha of xp reduced to the Legendre manifolds amounts to what? U is some coefficient beta, some function, function beta of what? Of a controlled entropy flux. Yeah, so what I say, I can compute the temperature of the thermostat, and actually that amounts, all the stabilizing controllers will be a function of the controlled entropy flux. And how do I see? So it's lambda E is the coefficient of it's a conduction parameter. And then I have the temperature of the thermostat, Te minus T2 divided by T2, because this is an entropy flux. Yeah. And what I need to compute is now the temperature of the thermostat. And this is very simple. It will be just the partial derivative with respect to the cell which is in contact with the environment of any potential, UD, desired, of x1, x2, the two entropies, yeah, of the system. Yeah? So basically, and this is classical for this way of deriving controllers, at the end, the control amounts to shaping a potential. Yeah? Yeah, it's not, of course, and that is somehow quite nice because very often you would like to do control design with your colleagues of chemical engineering or robotics, and they have a very precise idea what they would like in closed loop. Yeah, they would like the system to behave like. Yeah, yeah. And then that means that UD, I hope they can tell me what they would like as artificial thermodynamic potentials that you can add to the system. Yeah. So, but it's nice to prove that this is a result you get just by structure-preserving feedback. Yeah, and then you have, of course, to choose UD that the whole system is stable, but you know that you can necessarily. Yeah. So I don't know if I'm very much in advance, but I skipped. So. So there are still alternative formulations, like for electromechanical system. Yeah, I'm very fond of one of them. So what I have presented in the example is to use a one form which stems from the energy formulation. So du is TdS plus PdV plus mu dN. That means you write the balance equation on the entropy, the volume, and the number of moles. But this is not what is written in chemical engineering. What is written in chemical engineering is the balance equation on the energy. You don't like to write nobody likes to write the entropy balance. You can do that, but nobody really likes it. So you have an alternative formulation, precisely with all this control stuff, using the entropy formulation. And then you have in this paper of Balian and Valentin, you have a very nice relation between both formulations. And then Joachim Merker has generalized our definition of control system, which is the analog as for mechanical system, and I don't understand it. I mean, so I don't understand why it should be useful to me. I should be more precise. Yeah. And then, of course, yeah, with my dear friend Hiroaki, since now I don't know 30 years. We work together, and I'm very fond of Hamiltonian formulation and very fond of Lagrange formulations. And that continues because you have a number of people who suggest that you can either reduce or embed the system in a symplectic manifold, and then would prefer that. Yeah. So, okay, it's very interesting, I should say. But again, it's a matter of discussion and. Yeah. Yeah, and then there are a lot of things I don't understand at all. How to choose this contact Hamiltonian K? Yeah, so now I take P transpose drift as the vector field associated with the balance equations of extensive variables. But can I have an intrinsic characterization of an irreversible process, thermodynamic irreversible process with this function? I don't know. That means especially far from equilibrium, what can I do? there are a lot of questions. And then, of course, there's also the question of the continuity between the microscopic description and this macroscopic description. So Miroslav Grela has written different things on that, but that would be very interesting. I mean, that would be interesting to me to do that again. And that, I mean, really, I think we get a lot of ideas, yeah, on there. And then the port variables, the discussion is finished already? Yeah, and just this is, for my part, I like very much, I like now to define interconnection of system, but you see, if I have two contact systems, I take the product of the two spaces. I don't get so easily a contact space, yeah, but it's, okay, I think you can get out a situation. And feedback, that will be more my problem than yours, but it's very interesting. So I stop here because I'm late. Thank you for your attention.